In this lecture, I'm going to go over homework 7. Homework 7 was about this theorem that we've been discussing, and it's if you have two angles, alpha and beta, and you want to do a rotation about A by alpha and a rotation about B by beta in this order, so first around A and then around B, then this is the same as a rotation around some point C by alpha plus beta. Unless alpha plus beta is an integer multiple of 2 pi, and then this product of rotations is just going to be a translation. So let's go over this homework. The first homework problem in this homework 7 is to calculate all these values of f, where f is a rotation about a by pi halves, followed by a translation by b, followed by a rotation about c by pi. And then there's this part D where it wants you to find a fixed point of this function f, meaning that I want to find an xy that is mapped to itself by f. So some xy, such as f of xy is equal to xy. So first, let me write down what f is again. F is a rotation, first around 1, 1 by pi halves, then a translation by 1, 3, and then a rotation around 2, 4 by pi. So this is a quick representation of f, and I can eliminate most of the information then on this page. So we're first going to calculate this, and then we'll come back to these problems and deal with what they're asking us to do. So this is just to remind you what the translation matrix is and what the rotation matrix is. And this is our f that we had on the previous slide. And so what we want to do is to calculate what this is in terms of these matrices. And I just wrote down the product of these right away here. And let's just make sure. When phi is pi halves, we have cosine of phi is 0, and the sine of phi is 1. So we're going to get -1 here and a 1 here. And that's what I have here. So 0 for the cosines, and the sines are 1. And this is minus sign here, so it's -1. 0, 0, 1s, and then these two I have to figure out. But again, phi is pi halves here, so this is 0, and this is 1. And so we just have x1 plus y1. And since these are both 1, we're just going to get 1 plus 1, which is the 2 here. With the sine being 1 again, and the cosine being 0, this is going to be minus x1 plus y1. So it's -1 plus 1, and so this is 0. So that gives me this matrix corresponding to R of pi halves comma 1, 1. This is a translation matrix by 1, 3. Just see if I put a 1 and 3 here, it's going to look exactly like T sub 1, 3. Again, just putting a 1 and 3 there, and that's this matrix. The third and final matrix for this product is R sub pi of 2, 4 here, and so we're going to plug in pi. Cosine of pi is -1, so we have -1s here. Sine is 0, so we have 0s here. Of course, we have 0, 0, 1 like usual. And the only thing to look at then is the 4 and 8 here. With the phi being pi again, this is going to be -1. 1 minus a -1 is 2, so we have 2 here, and we'll have 2 here. Sine of pi is 0, so these are both 0. And so we just have twice x1 and twice y1. So twice 2 and twice 4 gives me the 4 and 8. So twice the x1 and twice the y1. So 4 and 8, and the 1 just comes from here again. So this is the rotation matrix R sub pi comma 2, 4. We want to multiply these and see what this looks like. So I'm going to start from the left. I'll multiply these two together first. So I take the 1, 0, 1, dot it with each of these to get the first row of the product. So 1, 0, 1, multiplying this by 1, this by 0, and this by 1 gives me 0. And then I'll have 1 times -1, 0 times 0, and 1 times 0, and that'll give me -1. Then I'll have 1 times 2, that'll give me 2, plus 0, plus 1, So that'll give me 3 when I do that dot product. So that's the 0, minus 1, 3. We do the 0, 1, 3 dotted with this, we'll get 0, 1, and 0, so that's the 1. Then we get 0, 0, 0, so that's 0. And finally, we get this dotted with this. We're going to have 0 times 2, 1 times 0, and 3 times 1, which will just give me the 3. And then finally, when we do 0, 0, 1 dotted with this, these are all be 0 here. We're just going to get 0, 0, 1 back like usual when we're multiplying these matrices. So that's the product of these two matrices. It gives me this one. And now I want to take this product. I'll have a 0, 0, 0. So again, I'll begin with 0. Write this down here. So that's the 0 there. Minus 1, 0, 4 dotted with this. We're going to get 1 and then 0 and 0. So that's the 1. Minus 1, 0, 4 dotted with this. We'll have a minus 3, a 0, and a 4. So that's just going to be 1. Then we take this 0, minus 1, 8 dotted with each of these. So we're just going to get minus 1 for the first one here. This dotted with this will be 0. And then this dotted with this, you're going to get a minus 3 and a plus 8. So that's going to make the 5. And 0, 0, 1, like usual, we'll end up with 0, 0, 1 here. So this is the product of these three matrices that represent what's on the right-hand side up here for F. So now we can think of F as being this matrix, the product of these three, this matrix, and we want to apply F to some xy. We're applying it to xy1 here. We just multiply and see the result. So let's look at this. We have F again, and that the product of these matrices gave us this. The problem we want to handle is we want to see what happens to some xy. And so we go ahead and multiply by xy1. And this is going to give us 0, 1, 1 here. So 0, 1, 1 will give me 0, y plus 1. If I take the minus 1, 0, 5, I'll get minus x, 0, and 5. So that's the minus x plus 5. And then 0, 0, 1 will be 0, 0, 1. So this is telling us that the function f is taking xy, a point xy, to y plus 1 comma minus x plus 5. Minus x plus 5, I've written here as 5 minus x, but it's the same thing. So this is then the value of f of xy. This is what f takes the point xy to. It's going to y plus 1, 5 minus x. So now we can look at the problems. F of 2, 3. X is 2, y is 3. So we're going to get 3 plus 1, which is 4, 5 minus 2, which is 3. So 4, 3. For 3, 3, we're just plugging in 3 for both of them. We'll get 4, 2. I plug in 4 and 5. We'll get 5 plus 1, which is 6. 5 minus 4 is 1. So 6, 1. And then the last question, part D here for number 1, is to go ahead and figure out what this fixed point is. Again, we want f of xy equal to xy. So we want this to be x, this to be y. So that xy goes to xy. So this needs to be x and this needs to be y. So we want x equal to y plus 1. And we want then y equal to 5 minus x. And so I want to put everything on one side, so I'm just going to rewrite these. So x minus y will equal 1 is the same thing as this. And this one we can rewrite as x plus y equals 5. We want to solve for x and y here, so I'm just going to add the two equations together so the y goes away. 2x equals 6. And then dividing by 2, we get x equals 3. Going back to one of these equations, say I take x equal to 3 here, y is going to be 2. And this should satisfy the other equation as well. I have 3 minus 2 is 1, so that's working fine. So the answer then is 3 comma 2. If I take 3 comma 2, again, and plug it into here, y is 2, so this becomes a 3. X is 3, so this becomes 2. And f of 3, 2 then will be 3, 2. And this was necessary and sufficient in the sense that There's no other answer here. I mean, these equations had to be true, and that's equivalent to this. And then we had to get x equals to 3, and once x equals 3, we had to get y equals 2. So this is the only point that's a fixed point for this function. F, there are no other answers. F of 3, 2 equals 3, 2, and nothing else satisfies this equation down here. So that's the end of problem 1. Let's look at problem 2. Problem 2 says to show that a translation by AB is the same thing as first rotating around the origin by pi, and then rotating around a over 2 b over 2 by pi. So this is just the same point we started with, but half multiplied by 1/2. So we have a over 2 and b over 2 instead of ab here. So in other words, we're trying to show that a translation by a point AB is the same as rotating about the origin by pi, followed by rotating about a over 2 b over 2 by pi. It's somewhat important here that these angles add up to 2 pi in some lecture that's coming up, the one I'm actually want you to view right after this one. So maybe keep in mind as you're listening to that these add up to 2 pi. It's in there subtly, you might not notice it, but it does come up that the translation is a product of 2 rotations by pi. So what we're trying to show is this, and let me remind you what we know actually. We know that the product of these 2 rotations is a translation because the angles add up to 2 pi, and 2 pi is an integer multiple of 2 pi. It's 2 pi times 1. So this is a translation. So the question is, why is a translation by AB? So one way to check that is if you know it's a translation, just see where the origin goes. What's happening to 0, 0? So the idea in this equation here is I'm trying to explain why if I take 0, 0, I'm getting AB. And once I know the origin goes to AB, that means the only way you can be a translation with the origin going to AB is if the translation is by AB. It's taking everything in the same direction as it is when you go from 0, 0 to AB, and that distance. So it's going in the direction and length of the vector AB. So if I can show that 0, 0 goes to AB, just knowing that this is a translation, it would have to be the translation AB. So that's what we're trying to show. Now, I don't really mean to be matrices here. What I'm really talking about is just do the rotation. So if I take 0, 0 and rotate around the origin, well, if you rotate around the origin, all the other points move. They're going to be moving by an angle of pi. So you're going to go around the origin by an angle of pi, but the origin itself doesn't move. That's the center of the rotation. So that's not going to move when I do this rotation around the origin. So that's why I left that out here. If I just do this part, I'm getting the origin. So I'm just back to having the origin that we're trying to rotate. Now we're trying to rotate the origin about the point a over 2 b over 2 by pi. And so you need to imagine being at a point a over 2 b over 2, and you look at the origin. What happens if I rotate the origin about a over 2 b over 2 by pi? It's just going to go the exact opposite side of a over 2 b over 2, the same distance from the origin. So it's going to go to AB. So you can sort of just picture this as going to AB if you just think about what these rotations are doing. So that is one way to explain why this equation is true. It's saying that these 2 rotations take the origin to AB, and since we know that this is a translation because the sum of the angles is 2 pi, then it has to be the translation that takes the origin to AB, and that is T sub AB. Another way is just to go ahead and multiply the matrices out. So this was the matrix explaining what one of these rotation matrices look like. And if I just go ahead and plug things in here, first the rotation about the origin by pi. Both of these are by pi here, so both of them are going to have a -1 and a -1 here, because the cosine is -1 and the sine is 0. So we have -1, -1, 0, 0 on both of these. 0, 0, 1 is the same as here. So what happens here, we did this in the last problem. Let's see, when phi is pi, this is -1, so we're getting 2x1, and this is 0. And here, this is 0, and we get 2y1. So we're getting twice x1 here and twice y1 here. So in the case of 0, 0, twice 0, it's just 0, 0. When we come to AB, we're going to want to put twice AB, A over 2, sorry, and this will be A, and then twice B over 2 will give me a B. So we have AB here. Now we just want to multiply these two matrices out. We see minus 1 times minus 1 is 1, and then we have 0 and 0, so that's giving me 1 there. Minus 1, 0a dotted with this, we're going to get minus 1 times 0 plus 0 times the minus 1 plus a times 0, so that's just giving me the 0. Minus 1, 0a dotted with this, well, we're going to get zeros for these because we're multiplying by 0, then a times 1 will give me a. So that's the 1, 0a. We do the same thing down here, 0 minus 1b. 0 minus 1b will give me 0. 0 minus 1b will give me 1. And 0 minus 1b here will give me a b. And then 0, 0, 1 will just give you the 0, 0, 1 back like usual. And notice then this is the matrix we have for the translation T by a T sub AB. So this is exactly the matrix we had for that translation. So we see then that if we do rotate around the origin by pi, followed by rotation about a over 2, b over 2 by pi, that viewing these as matrices, the product of these two matrices equals the matrix that's a translation by AB. And so we get, in fact, again, that this equation is true just by multiplying matrices. So that is two different ways of viewing this equation and how to prove it. And that finishes then what we needed to do for problem 2. So we finished this problem. Now let's look at problem 3. I'm going to put that right here because we want to start by using problem 2. So let me remind you what F was in problem 1. This is what F was. It was this rotation around 1, 1 by pi halves, followed by translation by 1, 3, followed by rotation about the 0.24 by pi. In this problem, we're trying to show that F is the same thing as a rotation about a point D by 3 pi over 2. So, and then we got to find the point D. But let me go ahead and comment that in the next lecture, you're going to see that something more general is true, that when you have a product of rotations and translations, all we have to do is look at the angles of the rotations, add them up, and as long as this is not an integer multiple of 2 pi, we're going to just add them up and it's going to be rotation by the sum of those angles. So this will be a rotation by 3 pi over 2. But you should think of doing this problem before the next lecture, and that we don't know the next lecture yet. And part of the reason for doing that is what I'm going to do in this problem is exactly what you need to do in order to prove that theorem. Okay, so this has to come first before that theorem because this is what we're going to be doing in that theorem that I don't really give a proof of, but this is the proof. So the question is, how would you handle a translation in the middle of all these rotations? And the answer is you take that translation and you write it as a product of two rotations like we did in problem 2. So we can take T sub 1, 3 and rewrite that as a product of these two rotations. What problem 2 said was if we have a translation by some amount, we can rewrite that as a translation about the origin by pi, followed by a translation about 1/2 of whatever this point was, so 1/2 3/2 by pi. So that's what number 2 was saying. And so using number 2, we get that this can be rewritten like this. So now we just have a product of rotations. And we could add the angles up, but we got to be a little bit careful here when we're using that theorem because we got to do it in the right order. If I add these two together or add these two together, I'm just getting a translation again, and that doesn't quite give me what I want. I want to be able to keep with rotations, so I'm going to group things this way. So I want to multiply these two matrices first, and then multiply by this matrix, and then multiply by this matrix. So the product of these two rotations by our theorem, you just add the angles. It's 3 pi over 2. So it's going to be rotation about some point by 3 pi over 2. So I don't know what the point is. I'm just going to put a star there to represent some point. I don't know what it is. So now I have a rotation about some point by 3 pi over 2 from the product of these two. And now I have a rotation here, this one right here, the rotation about 1/2 3/2 by pi. And I'm multiplying these two together. I add the two angles, I get 5 pi over 2. Now 5 pi over 2 is not an integer multiple of 2 pi, so this will be a rotation by 5 pi over 2 about some point. This is a different point, but I'm just going to put star there still just because I don't know what it is, but there's some point there. It's not going to necessarily be the same point, so it's really a different point. So that's what star is. It's just representing some point. But now you can see I want to multiply these two rotations together. This one's a rotation by 5 pi over 2, and this one's a rotation by pi. So I just add the angles, and I get 7 pi over 2. So I'm going to have a rotation about 7 pi over 2 about some point. Now, I want to go a little bit further because this is taking some point in the plane. We don't know what this point is, but somewhere in the plane, and you're rotating everything around that point. How much are you rotating? Where you're going 7 pi over 2, what is 7 pi over 2? Well, it's 2 pi plus another 3 pi over 2. Okay, so 7 pi over 2 is 2 pi plus 3 pi over 2. 2 plus 3 halves is 7 halves. So we're going to go 2 pi and then another 3 pi over 2. So when you go 2 pi, that's not doing anything. You're back where you started, but then you're going 3 pi over 2. So this is really just a rotation about some point by 3 pi over 2. In fact, the same point we have here will be here, even though these 3 points are different. This one will be the same as this one. We're rotating by 3 pi over 2 about this one because that's the same as going 2 pi and then another 3 pi over 2. So this shows the first part of the problem. We've shown that it's a rotation about some point, which I want to call this D in the end to agree with what's here. But whatever this point is, this is D. This is what we're going to call D. And this is a rotation about D by 3 pi over 2. So the second part of the problem is to find what D is. It looks like we left out quite a bit here to try to figure out what D is. Now we could write down these matrices, multiply them out, and figure out what D is that way. But there's an easier way, and that is the following. To use what we did in part 1. Remember, part 1, or problem 1, part D of problem 1, was to find a fixed point for f. And we showed that f of 3 halves equals 3 halves. That was the only fixed point. That was what stayed the same. If I take f of 3 halves, I got 3 halves. But now we know f is a rotation about some point by 3 pi over 2. And when we rotate around that point by 3 pi over 2, keep in mind that the only thing that doesn't move again is that center of the rotation, is the point D. Everything else is turning around D by 3 pi over 2, but D is staying where it's at. So the only fixed point of f is D, so D has to be 3 over 2. So we're able to conclude then that D is 3 over 2. And that finishes this problem because we've shown its rotation about some point, which we're calling D by 3 pi